Right. You didn't need to know any of that stuff anyway, so that's fine. Just need to get the problems right. So this problem I chose quite in particular because you may remember on the last test we actually suffered quite a bit, and this is profound. I'm really anxious that you take this in. If I say to you, hey, this skater starts from rest on this 22-meter slope, rolls down, cruises down, and lands. You know, we figured out where did they land, how fast were they going, and all that stuff. But my point is we're going to do it using the equations or principles of work and energy now. And it's way easier. That's the thing that's so cool. But you understand from what I introduced class with, that it's not different equations. Like we made these equations from the velocity and position equations that we had before. It's really the same. It's just this is going to speed the process up a lot, which makes it extremely cool and fast. So let's see if we can pull that off. And so we're armed with a couple of, you know, basic equations. And so, all right, well, first let's get from here to here. And again, as always, like interrupt with stupid questions. If you're not sure, please speak up immediately. So before we said it's like two different situations. One, they're cruising down this hill. And notice I called it a skater this time because it would be negligible friction. Not non-existent, but negligible if it was a good skateboard, good bearings and stuff. But then if we went from B to C, that would be kind of different, right? Because now they're not rolling down the hill. Gravity is kind of working in a different way. And so let's take a look at what happens from A to B first. But let's do it using this equation that I just introduced you to, saying, okay, cool, we have a certain amount of initial energy right now, perhaps. And then we're going to do some work on it. A force and a distance. And then we're going to have a different amount of energy later. So velocity initial, velocity final. So I want you to think about what's going on up there at A. What is what's my initial energy up there? What's my mass? How fast am I going when I'm up there? What? Yeah, you're not moving at all. Now, do you have to not be moving? No. You could have started up higher, and by the time you got to this spot, you could already have some velocity, right? But in our case, we started from rest. And so we really had no, I guess you could say, kinetic energy because we started from rest. We have no motion energy. All we have is potential energy because we're up the hill a ways, right? So sweet, that's what we're doing up there. That's why we're up there. We're skating. This is rad. And so, cool. So do I have a force? Do I have a distance? Yeah. But what is that distance? Well, you may remember that since force is mass times acceleration, my mass is 48 kilograms. I'll leave the units in there this time. And if I multiply that by the acceleration of 9.81 meters per second squared, I'll have kilogram meters per second squared. Hey, that's going to be a force. And I think that is, do I have that written down somewhere? 470, does that sound right? Yeah, it does. So that's 470.88 newtons. So there's my force. And then I have a distance. Well, how far does that distance work? I'm going to write some stuff in here, and I want to know if you can tell me what's wrong with this. Anybody know what's wrong with that? Isn't the force is 471. I found his force based on gravity. And then the distance there is clearly 22. What's wrong with that?
22 meters away every second.
That does change, but it is going to act for that 22 meters while the skater goes down the hill. But think about direction. Like, what direction are those? What direction are those in? Yeah. So the gravity is really kind of like that arrow. It's going straight down, but that distance is not 22. So would this work if I found that distance, this distance right here? It would. In other words, if I change 22 to whatever that shorter distance is, then it would work, 471 times that. Or I could take 471 as we did on the last test and convert it to kind of these two components, right? Isn't that force of gravity? I've got this component and that component. I could basically discover this one up here. If I found that force, then I could use 22 because they're going in the same direction. So it's kind of an important note that the work is a force and a distance, but they have to be kind of going in the same direction. That's not obvious, is it? I don't think it is anyway. So let's see, if this angle up here is 72, then couldn't I say since this hypotenuse right here is 471, couldn't I say that the cosine of 72 is equal to adjacent force divided by hypotenuse? Let's see, I think I drew this wrong. No, I didn't, I drew it right. Divided by 471. Wouldn't that tell me what that force was? I don't think I'm gonna write all this down, but like punch a couple buttons. If you take 471, and better probably go ahead and leave the right answer in there, 470.88. If you say times the cosine of 72, don't you get 145 point something? 54? That's close enough. So does it make sense that would work? 145.54 times 22? Now, just out of interest, as I said, this is kind of cool, but it would have worked to leave 471 in there, but then this would have to be my distance over here. Well, think about what that would be. Wouldn't that be, let's see, if I look at this angle here, 22 would be the hypotenuse and D would be this side. So wouldn't it be cosine of 72 equals adjacent, which is D over hypotenuse of 22? And so I could have replaced 22. In a sense, what I did up here is replace this with 471 times the cosine of 22. That's, I'm sorry, 72. But couldn't I have just, I'll erase some of this so it doesn't end up looking confusing, but couldn't I have also replaced that 22 right there with the actual straight down distance, which is 22 cosine of 72?
That's not really distance. Right.
So what that would be is the vertical distance then. That's how far it actually went straight down from A to B. Do you see what I'm saying?
Oh, yeah.
In the end, notice those are the same exact answer. You're actually taking 471 times 22 times cosine of 72, no matter which way you did it. That's what's kind of cool. You get the same answer either way. So let's see, what do I erase here? I'll leave it kind of the way that we've been doing it. And so that tells me about the potential energy I have. It's basically how far above B am I? And so now I know how much energy that is. We'll take a look at what's left on the other side. Well, don't I know my mass? Let's undo that. Don't I know my mass, we said, was 48 kilograms. And so does it make sense that equation now just has one unknown? So I have 145.54 times the distance of 22 on one side, and I have 1/2 times 48 times velocity final squared on the other. Hey, I'm going to get my velocity then. I'll know my velocity at B. In one sense, we worked a little harder at that the other day. So if I grind that out, I get 11 point. Maybe I should put B down here. Velocity final, at least at B, is 11.55. So this concept of energy, kinetic and potential energy being related to each other, just allows me to kind of figure out as I move from one point to another, sort of what's going on. Okay, sweet. Let's go now from B to C. And remember how terrible this was? Because we ended up having to have our velocity equations from our note sheet that we made and also our position equations. We had to solve a squared equation using the quadratic formula and all that. But think about how easy this is based on what we just discussed. So I'm moving now from B to C. Well, let's consider that same exact equation. So I'm gonna grab that dude. But now let's move from B to C with this. Well, does it make sense I have an initial velocity now? Because at B where I started, my initial velocity is 11.55 and I have my mass. That seems okay, it's 48. So I actually have initial energy this time, initial kinetic energy. Is there work to be done? Stare at the figure. Is there anything working on me when I go from B to C? Yeah, gravity again. And let's do this the easy way. Isn't gravity going straight down? We just said a second ago that it was roughly 471, right? I'll go ahead and write the better answer. And how far is it going? Exactly right. Notice I don't need to know the curve distance, which would be integral calculus to figure out. I can say, well, the force is straight down, the distance is straight down. And again, what this is really getting at is the fact that, remember, horizontal and vertical in projectile motion acted independently of each other. So that's exactly right. I can just say 6. And I know my mass, 48. Hey, look at that. There's an equation with only one unknown. That's rad. That's easy to solve. Please notice, like, how hard was this the other day? That was hard. Hard is it now? Not hard. This is really a cool concept. You see what I'm saying? So you don't need what I showed you today to get this right, but wow, that's amazing. So if you grind that out, I'll say initial or velocity final, and I'll say it's C, even though it's kind of under the heading, I get 15.85. Again, there might be some rounding errors there. And notice those two velocities are aiming different directions, and make a note of this in your mind and perhaps even in your body. Do you agree that when you left B, remember how this was really important the other day to know what direction that was going? Because we had to say, oh, okay, well then how much of that is horizontal and how much of it is vertical? Whereas down here at C, would you agree it's actually going this way? It's like two totally different directions. What's kind of cool about working energy is it doesn't actually care. It can kind of be going, it's just a reflection of energy. Speed is a reflection of energy. And so whatever direction it's going, it's got a certain amount of energy to it. So it's kind of like direction doesn't make any difference. Now think about this. For that matter, did I even have to do this in even 2 steps? Couldn't I have just fallen straight from A to C? Left gravity alone. In order to get the distance, wouldn't I have had to have kind of like that distance plus this distance? And I could just put that in as one distance. Would I get the same answer? Mm-hmm. Like it didn't even matter that one time it was rolling down a ramp and then the other time it was flying through the air. Now, of course, if there was friction on the ramp and we had friction problems, that's going to screw this up. Does that make sense? Like you would have to do them separately if the ramp was making you behave differently. But if you slide down the ramp without friction and you fly through the air without friction, then it does work. If you think of the friction sliding down the hill as wind resistance and flying through the air as wind resistance, then they're both the same. It doesn't really matter whether I'm kind of going straight at an angle or flying along a curve. That's kind of kind of fascinating. So this could literally be done in one step. Maybe I'm going to quickly write that out just while you process the magnitude of that amazing fact. One step. Actually, this is important that we do this. So the cool thing about starting from the top was, remember when you started, you had no velocity, so that's cool. Let's see, did I say this on the note sheet? Let me look real quick. Yeah, I did. See this right here? What's the symbol mean? Means the sum. In other words, there could be more than one force and more than one distance. There could be more than one work happening on it at the same time. In other words, this distance right here, I could add up both of those yellow distances, or I could just write two separate force distances. Does that make sense? In my case, I'm just going to be lazy and say we figured out our force was 471, and our distance was, we said I erased it, but we said it was the 22 times the cosine of 72. And then the 6 added on to it, right? And then mass is 48. Boom. One step. That's an equation that's only got one unknown in it. You might punch that in your calculator really quick. Remember, if you're going to multiply this like it sits because of the distributive law, you would need that parentheses around that, but type that in really quick. If you take that, 471 times that parenthesis, then you multiply both sides by 2, divide both sides by 48, take the square root. Bam. 15.85. Man, if I was good at this, if I practiced, if I understood this, I could be done with this problem in like 60 seconds. And it took like 30 minutes the other day, right? This is kind of cool. Again, this is humans inventing cool things. Pretty brilliant. So the concept of work and energy can be kind of a pretty powerful idea. How's your brain? All right. Is there any room left in it? Yeah, in the project when we were sliding the block off the table and you guys had the whole board full of stuff. Do you remember though, that was a little complicated by the fact that we tried to do it for real, which has made it so hard because there really was friction on the table, and that would make this problem not as doable. So as cool as this is, it's not, the ultimate answer all the time. But the one thing I want you to take away conceptually from this is it's really weird that I don't care how it got there. Like, does it make sense if it had been like a bee flying through the air or something and it was like going crazy and swirling all over the place? The fact that it started up here and went down there, that's all that matters. It's crazy.
With friction, you could still do it in two parts of it.
Yeah.
So
Could you still survive friction? It's you have all these brilliant ideas, Ian. How could you get friction involved here? Isn't friction just another force? Yeah. It's just the sum of the forces, right? So there'd just be another force, like it'd be a force against you, right? So before we said, oh, a grand total of 145 was kind of what pushed you down the hill, right? And so we said, hey, that pushed you down the hill 22 meters. Well, wouldn't there be a force of friction against you also for 22 meters? Yeah, so it's not that you can't use this for friction. Brilliant. Brilliant. So the fact that, and this is the only other example we need to do, which is good. What time is it? In terms of at least this section. If you look at this question, these problems were tremendously complicated as well, because now the person is not falling in a parabola. Remember, we had equations that worked for parabolas, for parabolic flight, and then we're okay with straight lines. But when something is really strange like this, and notice they're saying, hey, that's a cosine wave. Notice that's a chunk of a cosine wave, which again is pretty unrealistic, right? X Games, somebody mapped a cosine wave out there in the snow to make this happen. That's kind of unrealistic. But notice we kind of like, conceptually, we like the energy concept here because the energy doesn't care how it got there, right? It started at this high and it ended at this high. Awesome. So I don't care that it went down some curve. That's kind of my first thought. So stare at this for a second rather than just immediately starting to do it. It's like, what's going on in the 150-pound skier? I'm going to think out loud with you a little bit here. Oh, pounds. Hey, cool. That's already a force. I don't have to multiply by gravity. Our system, that's already a force. So that's a force. That's his force. He's at point A. I'm making notes to myself. Oh, he's at the top. So that makes sense. He started at the top of something. And he already had a speed of 5 feet per second. So that wouldn't have surprised me if it said he started there from rest, right? But remember, he may have came from what's before that, like a bunch of rollers. And so he already had some speed. He already had some energy right when he got there. He already has some energy. Cool. And then he's going to ski on down the hill to this point he's at right now, at point B. Do you see the energy and work happening there? Like he already had kinetic energy, he already had velocity when he started, but then gravity is going to pull down on him, right? And increase his energy. So because he's at A with already some kinetic energy, so thanks to his speed, but being at A, he already has potential energy too, because he's above where he's going. Does that make sense? So does it make sense that, I'm going to erase this, but if a skier was over here, when he got to the bottom right here, he would have some speed thanks to the hill he came down. But notice now he's getting work, it's working against him, if you will. Does that make sense? Now the work is actually going to slow him down because he's going against gravity. But in our case, he's actually speeding up. And so do you see the concept of, does he already have some energy, mv squared, energy based on speed? And then the question is, okay, now he's going to travel from there. If he goes up, then gravity's working against him. Work is going to slow him down. He'll be going slower later. But this, like the previous example, he's going down, so he's actually going to go faster. So, okay, that makes sense. So my first thought is like, and I sort of purposely try not to study these questions ahead. My first thought is like, I don't care. Like, why did you tell me that equation? I don't care. A second ago, he went down 6 feet, right? I don't care. Just how far is it? If I know this distance right here, if I know that distance right there, then I don't need that equation, do I? Because don't I know gravity's working straight down on him and he fell that far? I don't care that he went down a curve. This is great. So why did they tell me that equation? It's like, I don't need to know that. And so they said, determine his speed when he reaches point B. What's this code for again? This keyword that shows up in a lot of these problems. When they say smooth, what does that mean? It doesn't just mean there's no speed bumps. It means no friction. Yeah. Again, somewhat unrealistic. In this problem though, and like what Ian just said, if there was friction here, which there would be, you would have to figure out how far he traveled, which would be a calculus problem because he's now traveling on a curve. And so you'd have to literally find that distance to know how far that friction worked on him, which again is kind of cool to think it can be done. Isn't that amazing? Like we're ignoring it, but that's just them being nice. But it could be done. Okay, so I need that distance. So they tell us it follows the cosine curve down. Oh, now I see. That's why they told me that equation, because that's the only way I have to get the distance. Like if they just told me the distance, I wouldn't need it. But they told me the equation because then I could actually calculate that distance. Does that make sense? So I guess I did need to know it in hindsight. Typical kind of a book problem, right? But if you're out on the slope, could you just measure that? You take some tools, but couldn't you just measure it? Do you need to know it's a cosine wave? No. If you're designing something in the X Games and you had some sense of, how the friction in the snow worked in a rough, even if you just made a rough measurement of the weird undulations of the snow, and you knew kind of what that was going to do to slow them down in their progress from a height to a depth. Tape measure will do it. Don't need an equation. So I think what makes physics hard though is seeing if you're given this problem on the street, you know, would you think of this as a work energy problem? No, I wouldn't. For me, it's like, oh, chapter 14. This is in chapter 14. What are we studying in there? So you need to look at this as kind of a bag of tricks that you have, and in the end, that's kind of why that note sheet is cool. If I attack some problem in life, I'm not going to know. I'm not going to know what to do. I'd probably try everything and just sort of see what shook out. And I'm good at this stuff, right? I've done this more than once. You're just learning it for the first time. So I'm going to give you a second. If I say, okay, cool. If I have an initial amount of energy and then I do some work on it, then I'll have a new amount of energy. Maybe it'll be less. Doesn't always have to be more, but it's going to be more in this case. I'm going to give you a second to kind of play with that a little bit and see what things you can fill in. Warning, mass is really tricky here. Remember how excited I was? Yeah, he's 150 pounds. That's awesome. I don't have to screw around with that. Is 150 pounds of mass? Like, there's some tricky stuff here. But I'm going to give you a second to, I don't know, screw this up perhaps. Because then whatever I show you will mean something more to you. You made it. Started without you though. Also, I forgot to record the first part of this, so. Oh, I want these equations right here.
I don't know what I'm about, but.
Students in the classes like Michael, no, everyone else is skiing, have done all of this stuff. I'll catch you on the next slide. I can't hang out with you anymore.
So in case you got the early boot, what did you do for mass in this situation? Let's just all make sure we agree on that. What is it?
I converted to kilograms. I didn't use force equals mass times acceleration. I just know that 1 kilogram is 2.2 pounds.
Yeah, in other words, you said, let's just do this in metric because that'll be easier. So I'll convert his weight to metric. Now that's fine, but you'll have to convert other stuff because you have, let's see, like his speed is feet per second. You have to convert that to meters per second. So you got to be really careful to do that. That absolutely will work. But take a look at this equation. If you need to know mass, if you solve this equation for mass, isn't it force divided by acceleration? So, well, his force is 150 pounds. And the acceleration of gravity in this world is 32.2 feet per second, right? So you could just put that in. Whatever 150 divided by 32.2 is, I guess that would be his mass. Again, isn't that weird? Like that's not cool, is it? So my first thought was, yes, I weigh 150 pounds, I actually understand that. But anytime mass shows up in a formula, actually the metric system is a little better. Isn't that kind of strange? And then what's up? Is it slugs? I'm pretty sure it's slugs, which is not something you've ever used. You guys have phones? What's the unit for mass? Talk to your phone. I think it's slugs. I'd bet your life on it. Not mine, but yours. I'd bet something. I should know that for sure. And he had initial speed of 5. Again, I'm being a little lazy, feet per second. And it's by the way I write stuff, because I love seeing the original equation. A lot of times I'll forget to square it, even though it's kind of sitting there, because it'll have it down below to be multiplied and I'll forget the squared.
It is a slug.
Slugs? All right. You didn't die. See ya.
32.2.
What was the symbol for it?
In order to get.
Yeah. Yeah. You guys haven't seen the symbol, it's a slug. You just draw a little curving thing. I have no idea. I'm making that up. I must have earned your trust if you believe that.
All the math is done.
Now, although that was pain, of course, he's got a force of 150, right? Don't have to mess with that. Remember before we had to multiply by 9.81 to get 48 kilograms. So it's like you have to do it no matter what. We just didn't have it so easy in energy, but now we got it easy with potential energy. So, wow, I'm almost home free. Like this is, if I come over here and stick mass in as 150 over 32.2, the only thing I don't have then is that first distance. And that's where I've got to go to this equation a little bit. So if I go over here to x is 0, right? Because notice this equation is y as a function of x. I sort of have to know how high I am. Little partial review of Math 112, but you might remember that the number in front of cosine right there has an effect on the way the cosine wave works. And the number in front of x also has an effect. The number in front, 50, is actually the amplitude. That's how tall the wave would be. And then the pi over 100 actually changes the period. In other words, how long does it take to repeat itself? You don't need to know that. But watch what happens here. If you put 0 in, cosine of 0 times pi over 100, that's a cosine of 0. Cosine of 0 is 1. I mean, you just stick this in your calculator, but you get 50. And so if you knew 50 was the amplitude, then you could have just known 50 without even plugging it in. That's kind of cool because it's the top of the curve. So, oh, okay, I'm 50 feet above the ground, the x-axis, and then I go back and say, okay, well, cool. What am I when I'm at 35 feet then? Since that's obviously my next location, how tall am I then? Of course, I'm staring at the graph expecting something less than 50, right? Because the graph shows I'm going downhill. So when I punch that in, let's see, degrees, radians. Suddenly wondering if that matters. Because we're almost always in degrees in here. Yeah, there's a pi in that. So I'm thinking I got lucky for that to occur to me, if you will. Do you agree with that? And if you were in degrees, if you just wrote it down and you're not thinking, that's why I'm always encouraging guys to be reasoning. Before I even push buttons, I'm thinking, oh, surely I'm going to get something less than 50. Look at the picture, it's shorter. But maybe if I'm degrees, I get some wonky answer, but then I'm smart enough to go, oh, that can't be right, instead of just writing it down. But yeah, I think Tristan's right. There's a pi in it, which means I think I actually have to be in radians here, which would be annoying. That would be the kind of thing on a test I would take very few points off. Although, remember, your job as an engineer, it doesn't matter what happened. It doesn't matter why. Everybody died. So you're not in radians. Sorry, that's not an excuse. So you punch all that beauty in and you get like 22.7 feet. Do you agree with that? So just to make sure I don't screw this up then, I'm 50 feet tall here. And I'm 22.7 feet tall there. So obviously D then would be the difference of those two things. So that means D is going to be, what is that, 27.3? So again, I'm happy with this equation because it's only got one unknown. It's got the velocity final unknown. Always a good idea to stare at and being a little footloose and fancy free with units, right? I didn't write all those things down, but 150 is pounds and 27.3 is feet, so that's foot pounds. So that was one of our measurements of work. Work was foot pounds. Okay, that's cool. Just for the fun of it, even though it won't be fun over here, let's do this. So I get 150 pounds over 32.2 feet per second squared. And then I'm multiplying by velocity, which was 5 feet per second, but it was squared, so I have two of them, 5 feet per second. So I'm just kind of curious, will I end up with foot pounds again? I should, right? The world is okay. Let's see, so what happens there? This foot cancels with that foot. Because this is a fraction right here, these second squareds are going to end up on top. Do you understand that? By reciprocating, by multiplying by their fraction flipped upside down. So both of these seconds will cancel with both of those seconds. Hey, look at that, foot pounds. It's kind of cool. So if I was a good teacher, I would take points off and make you show your units and stuff all the time, but I'm just talking about it, conscious of it, thinking about it. So sweet, I solved that equation for velocity final. I'll even say velocity final at B, and I end up with 42.23 feet per second. So that seems reasonable. Started at 5, went downhill 23 feet. Looking at this room, it's like 10 feet tall, twice that tall. I was already going 5. I went 20 feet down and I sped up. Doesn't mean I'm right, but if I'd have got 36, I would have thought that was probably right as well. If I'd have got 150, I might have thought, well, that seems kind of large. But it seems reasonable. So with respect to, X Games related stuff, because if he's about to go off of a jump, that speed that he generated right there would totally determine what's going to happen, right? Like where he's going to land. So I got to put the landing in the correct spot. Now that I know his speed, sweet. And I kind of know everything I need to know about that. That's kind of awesome. Notice though, that's not the only question they asked, which again, this author is pretty good. That's a good question to ask, but he asked the second question here, which is also, what is the normal force on his skis? Because we talked in the last section about how, you can be in some places where that force pushing you on the snow is so large that you can't stand up, or so small that it's negative, which means, oh, I'm flying, right? That was part of that project that I don't have from any of you until after class, right? So that normal force is kind of an interesting question. Did you have a question or comment? Yeah. We should have time. This won't take too long. Now, again, I'm reading this kind of for the first time. I haven't thought about it ahead. I'm thinking to myself, let's see, normal force. What is that again? It's kind of like that force. Normal to the snow, perpendicular to the snow. It's like the snow pushing on me, right? So that's a normal force. So then I'm thinking, oh, do I have to do this some of is this the tangential normal? Like, are they making me kind of go back to the previous chapter here? Is there, I don't think there's any way around that because they're asking me to kind of consider these two axes, right? So the blue is the tangential axis, the axis that I'm traveling in at that moment. And the normal is perpendicular to that, pushing against it. I think I'm having to go back to previous chapters. Do you agree with that? I'm not totally sure. Like I said, I purposely try not to do these questions ahead of time or refresh myself so that I can kind of just think with you out loud. So, I'm dredging up my memory. I'm just thinking things like, in this direction, that's the direction his velocity is going. That's positive. So this is positive direction toward the center of the curve. Remember, this is curve. So this direction going this way is actually positive, right? So I've got kind of my tangential axis and my normal axis. And I know what positive and negative is and so forth. So it's like I got to convert to that system. In order to get in, I'm going to have to convert to that axis. So yeah, I think I have to go all in on this. So let's see, what do I know? I know my weight. And again, I'm happy to be in our system here because I can just say 150 and I don't have to multiply by gravity. So that's 150 pounds.
You know your velocity at that point.
I know my velocity over here. My velocity at B, we said was, and maybe that's helpful. Maybe I don't need to know that, but let's at least write it down. So that's the velocity going in this direction. But don't I need to convert? Like the 150 is not in the right world, right? It's not going in the directions I need it to go in. Don't I need it to kind of go? Yeah. Don't I need to go like that and like this? I need to convert it so I know how much of that 150 is in each of those directions. What does it usually take for me to know that?
You need an angle.
I need an angle, don't I? But I don't have an angle, right? How do I get one?
The inverse tangent of y prime of x from our
Yeah.
equation. And since we know the x, under the line, just plug in x and we'll get the number.
That's exactly right. I can know the slope at any point thanks to calculus. So I could take the derivative of that, plug in x is 35, and I would know my slope. So it's like, yeah, there's that. But then I'm just randomly thinking here, but isn't like this the acceleration normal was v squared over rho? So I'm thinking, okay, that's one of my tools that I have. And then I've got that complicated. What do I do?
We can factor a in and then do all the forces in the normal direction, or equal to mass times a n, solve for n on for the normal force that the cell is applying.
Yeah, and I got the sum of the forces equals mass times acceleration in tangent and in normal. So I've got kind of those tools. I mean, it seems like I have to know the angle, don't I? So don't I? I think I don't have a choice but to kind of do calculus. So, as a math teacher, I would say, it'd be cool if you could take the derivative of cosine still, but that's a little foggy, right? But as an engineer, if you just need to know the slope when x is 35, what's the way to cheat?
Your y divided by your x. 22. No.
You got to know that, remember, the slope is constantly changing. Up here, it's one thing, it's just constantly changing all the time. So I need to know it exactly at 35.
It's the y over the x.
Should teach you some calculus. Like, don't you know the coordinates of B? It's over 35 and up 22.7. That's where it's located, right? So does it make sense I could just let him move a tiny bit? Like x is 35 feet right now. Couldn't I let him move to x is 35.1 feet? Just let him move a tiny bit and then plug 35.1 into that equation and get the y. And then I could go y minus y over x minus x and get a pretty decent fake of the slope without even knowing calculus.
But would that be like accurate?
Accurate enough. I mean, we're just trying to get an estimate here, right? And so, and it doesn't have to be 35.1, it could be 35.01. 0.01 feet, that's not very far.
It just has to be in the vicinity of that B.
Or go to Desmos, type in f of x equals 50 cosine pi over 100x, and then ask Desmos, what's f prime of 35? It'll just tell you. That's what an engineer would do. Your graphing calculator has dy dx in it. You would have, if you had my class, which a lot of you did, you can type that equation in there and ask it what dy dx is at 35. So you can cheat to get the answer to the slope here. But you know, you guys are math nerds. You're nerds. You're the kind of guys that are going to calculate stuff instead of actually skiing. Right? That's what we do. So anybody with a better memory than me, what is the derivative of cosine? That's something you either would have memorized or you don't. Yeah, sine. Negative sine even.
And then you
Derivative of cosine is negative sine. And the 50 comes along for the ride. And whatever the junk is inside stays unchanged. So derivative of cosine of junk is negative sine of junk. But then chain rule said you also have to multiply by the derivative of what's inside. And since the derivative of junk times x is just the junk, then that's the derivative right there. Now I could clean that up a little bit. Call it negative pi over 2, since 50 over 100 is pi over 2. And if your calculator is in radian mode, and you stick in x is 35, the advantage of real calculus is you get the perfect slope. You know, we nerd out about stuff like that, but engineer types, people that are building the X Games jumps or whatever, they don't care about the exact answer. So if I stick x is 35 into that equation, y prime is the slope, right? So however I get it, I get negative 1.4. But again, stop and stare at that. Does that make sense in the picture? A
Yeah.
slope of negative 1.4.
It's using the coordinates of X and Y.
Yeah, from here, negative 1.4, the slope is a rise and a run. I can put any number over 1. So if I rise negative 1.4 and I run positive 1, then that would be my slope. Oh yeah, that's kind of that's what I got here. So that actually looks reasonable, doesn't it?
Wouldn't we have to have it in degree? Right?
That's right. And so since slope is rise over run, the tangent of theta would be rise over run. So if I wanted the angle, I could say inverse tangent of negative 1.4. And again, this is a tricky problem because I'm probably in radian mode from the previous example, right? So if I actually wanted the angle to speak to me, I'd have to go back to degrees. There's no reason you couldn't leave it in radians, but your answer will just look kind of weird. So you could come up with that angle. So one of the things I've tried to kind of illustrate in this class is like, I find this hard too. I think about all the tools I have. And, you know, one of the things since we just got done taking a derivative, I'm thinking, didn't we calculate this radius of curvature using a second derivative? And so I already know my velocity. And if I could find the radius, I could find acceleration normal. Like, I don't know if I need it. Maybe that's a waste of time, but you're not, unless you're a professor of this stuff, you're not going to be able to do this in some kind of a step-by-step way. You just look at the tools you have and figure out everything you can figure out. You may need it, you may not, but either way, it's just figuring out cool stuff. So because that occurs to me right now, I'm going to drop off on that tangent really quick. No pun intended. Actually, I think I'll just, in the interest of time, if I take the second derivative and I stick 35 in there, I get negative 0.0224. The derivative of sine is cosine. So I could make that calculation and so forth. So now I actually could figure out rho for what it's worth, the radius of curvature, which if I remember right was 1 plus the derivative squared And then I raise all of that to the 1.5 power. And I divide that by the absolute value of the second derivative. Wasn't that it? Just going from memory. Maybe I'll go ahead and throw the negative sign in there. This is one place where, interestingly, you actually need that absolute value concept. If you do that, you get 227.35 feet. So if I stare at this picture for a second, given that I know what 50 feet looks like, does it look like the radius would be way bigger than that where you are? The radius is 200 feet. Notice it's pretty straight. It's pretty straight right here, isn't it? Wouldn't that be a monstrous circle? He's on a monstrous circle at that point. So I don't know if 227 is right, but the fact that it's that big kind of feels good, doesn't it? Feels reasonable. And so I guess I could find the acceleration normal now. We said his velocity was 42.23. And that's squared divided by this radius that we just got. Acceleration is feet per second squared. So I figured that out because it's cool. Maybe I don't need to know it. We did use a lot of these, I remember, in those previous equations, though, so it won't surprise me if I need it, but I don't know. I have all the derivatives. I have the slope. I have the angles. Let's see, I haven't figured the angle out yet. I'll write that up here. Inverse tangent of negative 1.4, you get negative 54.5 degrees. That feels, and again, I can stare at the picture and kind of say, yeah, that makes sense, because straight across is 0. And if I went negative 54 degrees, that would be clockwise. And so, yeah, that looks right, doesn't it? That agrees with that negative slope that we said earlier. So I think that makes sense. So yeah, this actually does look like it's a full on kind of, that was a hard question. The first question was actually pretty easy, but like when it goes back to what we did before, this is pretty hard, right? And so I'm thinking, okay, am I going to need the sum of the forces tangential is equal to the mass times tangential acceleration? Is that the right formula? So it's bothering me, is that right? Some of the forces that are normal.
Do we really need that one?
I don't know. See you, Navarro. Thanks for coming.
Yep.
So it's like, I don't know, I'm just writing down tools. So, you know, part of me thinks, hey, I just found acceleration normal, like that's part of that second equation. So maybe that's useful. But notice it's asking for forces that are tangential and normal. And so that kind of takes me back to this place. Like what we said earlier is I really do need to know that angle, don't I? Because I've got to convert that 150 into its two components, if you will. So I think I'll do that right here. So it's kind of good to draw these as I did in the picture. In other words, this is the component kind of in the normal direction, and this is the component tangential. But if I was to actually draw this kind of in the same figure over here, kind of in the head to tail approach that we took in statics, it would be something like that, right? So this is my 150, and I need to know those other two, but of course I'm struggling with, wait, what angle, like what angle do I put where? So that this is where I got to go back to my logical understanding of this problem, where I said, hey, this angle right here was 54.5 degrees. Notice because I drew it in the picture, I don't necessarily have to write the negative. Be okay if you did. You can write it or not write it. But it's like it is the angle between here and here. And since the angle between here and here is 90, then that means I could know this angle, which is the same as the angle I have. And so I guess that'd be 35.5. Does it make sense? This angle right here would be 35.5 degrees. And so armed with that, I could know what the forces normal and forces tangential are. So if I take 150 times the cosine of 35.5, I get 122.1. So that 150 pounds, 122 of it are devoted to sending him down the hill. Does that make sense? That's what's making him go faster. Not all 150 is making him go faster because he's not falling straight down. It's the same principle as when he was on the hill. I got to decide how much of it is devoted in the direction that we're going. So 122 is in the direction that we're traveling, but then some of it is pushing into the hill, right? So if I said the sine of 35.5 is the opposite over hypotenuse, I get 87.1 pounds. So if you will, this is sort of like a force that is normal, whereas this is a force that is tangential. So I've now converted gravity to the coordinate system that I'm stuck with at this point. And so I do think these equations, I'm going to copy this down below. I do think these equations are going to need this. So let's just see. I don't know. Again, I still don't even really know. I don't know where I'm going. I don't know if this is going to help me figure anything out. I kind of forgot even what it even asked me. I don't even know what I'm doing anymore. I'm just kind of taking the equations that I know exist and just trying to figure some stuff out and see where it goes. So force is tangential. Well, I've got, let's see, I suppose I need to have a free body diagram. Some of you didn't do a super good job of this in the last test. I've got this 122 going in this direction. And notice the arrows are really important here. I've got this 87.1 going in this direction. I've got the normal force of the snow going in that direction. So the bottom two are gravity, the normal force is pushing against it. Making a note to myself, this is tangential and this is normal. Okay, I think I got everything now. So what are my forces tangential? I just have 122. 122.1. And I've got a mass. Remember, mass was ugly here, 150. Excuse me, over 32.2. That's my mass. Oh, that's cool. I mean, I don't know if I need to know it, but I found the acceleration tangential now. Like I said, I've kind of forgot what I was being asked, but it's an equation with only one unknown. That's worth something. So punch that in and I get 26.2 feet per second per second. What does that tell me? Like, let's stop and stare back at the problem for just a second. What does that tell me about the skier? What is it? Why is that kind of worth knowing?
The tangential acceleration,
Yeah.
how much faster you're going, how much you're accelerating, and the
Yeah,
direction you're going.
that's exactly right. Remember, he was going 42 feet per second. And this is saying 1 second later, you're going to be going 26 faster than that. Whoa. Now remember, that's changing on a curve every second. So that'll only be an approximation because he's not on a straight line. He's on a curve. So that acceleration tangent will not be the same a tenth of a second later, technically. But that's kind of like, whoa, that's rad. 1 second later, he's going to go 26. He's going like, man, he's suddenly going to be going like 68. He's going 42, and 1 second later, he's going to be going 68.
We did need that.
So that's cool. I mean, they never asked me that, but who cares what they asked? This is kind of cool to know. I want to understand this.
What is rated with increases.
Did they ask that?
Yeah.
Sweet. Then we did need to know that. Down here, I got forces normal. Again, you got the positive negative problem. these two forces that I drew up here, normal and 87.1, which one of those is positive? Which one of those is negative? I should have actually had that in my figure. Remember, toward the center of the circle is positive, so this is actually positive, and the normal force is away from the center of the circle. That's actually negative. So those are my two forces. In this case, there are two of them. 87.1 minus n equals the same exact mass times the acceleration normal. I'm not happy with this equation because it's got two unknowns.
Well, you do have an.
But all of a sudden, that work I put in earlier to find AN is like, oh, good, I did need that. That's kind of nice. I'm glad I made it. And so now I can throw that in. And that's actually good news because now it's an equation with only n. And that was one of the questions they asked me, like, how hard is the snow pushing on you? Hey, that's cool. I can actually solve that now. So my random wandering, if you will, of just trying to figure out everything. You see what I'm saying? I mean, I've said this a number of times, but it's just something that's so important for how the real world works. It's problem solving. It's not, very few people just immediately know, oh yeah, there's 8 steps to this, and here's the order. Who thinks like that? Who can do that? You gotta be like Rain Man. That movie's too old for you guys. Rain Man. Okay. So if I punch that in, I get 50.6 pounds. Can you squat 50 pounds? With one leg tied behind my back. So it's like, that's good news, right? Like, I'm not going to crash. I'm not going to fold under this pressure. So that's kind of cool. It's positive, which means I'm still in the snow. I don't know if I'm happy or sad about that. But again, these are neat numbers. You see what I mean? In a practical sense, this isn't just like, oh, I got the dumb physics problem, right? So what I find when I'm all, just done randomly thinking like this is I can go back and I'll probably have every answer that I was asked for and maybe some more, right? Yeah, so I like the way they worded this, and I hadn't even got around to reading that question that you pointed out, Ian, but it asked for the increase in speed. That's tangential acceleration, not normal acceleration. If it said, what's the acceleration? That would have been a trickier question because you actually have to do the Pythagorean theorem on the normal acceleration, which is changing your direction, and the tangential acceleration, which is changing your speed. And so that's really a T. This normal force is what I called in. Hey, yeah, look, we figured everything out. And this is kind of I like this question because it's so close to being something realistic in a sense. Like you know everything about this person's motion, where they are, how fast they're going, how hard the snow is pushing on them. And this is really cool. So, quick side note, and I'll shut up. So, Sunday, I want to not bike ride, and there's this double. There's this double one that wanted to jump, but I can never. It's long. Like it feels too long. So anytime I come up to it, I always push the brakes on so that I kind of land right here, and then I roll over that next one. And I'm always trying to just get up the courage to just go for it. And so I did it like twice, and I did that. And the second time, I'm like, screw it. I don't care if I crash. I don't care what happens. I'm just gonna rip. So I went ripping up to it, but there's some stuff in the front of it that makes it so you can't just have whatever speed you want. So I did not get enough speed. I mean, even though I kind of rolled at full speed, I did not have enough speed. And so I just took off anyway, flying through the air. And as soon as I got in the air, I already knew what was going to happen. I literally landed right there. So my trajectory was like that. Notice that's perpendicular, which is like the worst that could possibly happen. And I mean, I kind of yelled as I was going through the air because I thought I'm going to get mutilated because I was going pretty fast. Basically just came to a stop and I kind of yelled out, and the forks completely compressed all the way down, and I was effectively bench pressing at that moment to keep my face from going over the handlebars or going into the handlebars, all that kind of stuff. And I just went, rah! And pushed, and I didn't crash, but it's like the next day, like all my muscles right through here all sore from exactly that normal force. I mean, can you imagine if I calculated, this is exactly why I say, you know, this is somewhat realistic, because I could calculate how much normal force that hill put on me right there based on exactly what we just did.
It's a new max.
And it would be like more than my max bench. And one of the things we'll talk about in a couple of weeks is the forks actually have the effect of taking that normal force and distributing it over a time period. Does that make sense? So it allowed me to bench press it over like 1 second, let's say, while it compressed itself instead of instantly. Because if it had been instant, the impact of that is the word we'll talk about in a couple of weeks. It would have been like trying to bench press 1,000 pounds for like 1/10 of a second. But because it was 1,000 pounds over 1 second, it spread it out enough that I ended up not crashing, which is what forks are really designed to do, which is kind of rad. And so this business of normal forces and all that kind of stuff is really kind of cool. You are powerful if you can solve a problem that's this difficult. But doesn't that feel kind of like given how hard the rest of that was, doesn't that feel kind of like a final exam question? Like the entire class is one question right there. And if I could get that right without making any stupid mistakes, that'd be a miracle. And then if I could conceptually, my only shot at being able to get it right would just be to stare at all my formulas and just start saying, okay, well, I got all these algebra formulas. Let's just start plugging in everything I know to every one of these formulas and figure out everything I could possibly figure out. And notice we never used any of the velocity position equations, but it's like maybe I could use those too. I don't know. But I will say the one difficulty of the velocity position equations is the fact that I'm actually traveling on a curve here. Does that make sense? That kind of screws that up. Those other equations were for straight line distances, not for curved distances. So one big takeaway from this class that's really powerful that I think takes a while to settle on you is these two statements right here. Linear and curved. If I'm curved, I have to create a tangential normal frame of reference, and I can only calculate stuff at one point. And as soon as I move to another point, the axis has changed. So if I see curves, then I'm in a different world. Notice these equations live in the straight world, and I wasn't straight, I was curving. And so I would not have had success using those other equations because I wasn't going straight. So kind of a powerful concept. All right, you guys are studs.